So let's continue, guys, with section 2H, problems 2 and 3. So this is the first problem about a TV. You're buying a TV, and the problem tells you the amount P paid for a new TV is given by the formula P of X equals 1.10 times X minus 25 for X greater than 25, where X is the original price of the TV. Okay, and the first question is this: state the component functions and explain what they might represent. Okay, so in here I wrote the same function. The domain x has to be greater than 25, right? Because otherwise this function wouldn't make sense. It doesn't make sense to pay a negative amount of money, right? So that's why x has to be greater than 25 so that this factor here is positive. And x is the original price of the TV. Okay, so what they mean by this, guys, by stating the component functions, they are talking about the component functions of this function. They could have been a little more explicit. State the component functions of P and explain what they might represent. This is, guys, this function, this is a composite function, if you notice. Okay. Uh, why do I say so? Because P, this function can be understood as the following. If I have this function t of x equals 1.10 times x, and a function d of x equals x minus 25, I'm going to explain the reason for the t and for the d in a moment. Then p of x can be understood as t of d of x. You see? So p of x is actually a composite function. It is a composition of t with d, t of d of x. And if you want me to convince you, then just do this. Evaluate t in d of x, which is x minus 25. And then this is the function. Evaluate it in x. Now all you have to do is evaluate it in x minus 25. And you're going to get this. 1.10 times x minus 25. And that's p of x, which is the same as this. You see? So this is actually a composite function. It can be understood as a composition of t and d in that order. Now, do they have to be called t and d? No. The name of the function makes no difference, guys. You could have called them f and g or whatever. It makes no difference. Okay, and then the second thing that they ask me is this: explain what they might represent. Okay, and this is actually this in this other question, in this second question, you have freedom to interpret what these things could mean. I wrote T and I wrote D because, as I understand, for example, let's talk about this function first. I understand this function x minus 25. If you know that x is the original price of the TV, then what could something like this mean? To me, this could mean a discount. You see, of 25. Let's talk dollars, of $25 over the original price of the TV. Why are they making this discount? I don't know. Okay, in the store that you went to buy this TV, I don't know. On a given day, they have a discount of $25 on all TVs. Okay, then in order to calculate the discount, the function discount of this of any TV, that would be the original price minus 25, and that would be the new price with the discount. Okay, you see what I mean? So that's why I'm calling this function D for discount. You see, it's kind of like this is gonna give you the new price, the cheaper price that you're gonna pay after the $25 discount takes place. That's all it means. But that's my interpretation, guys. You see what I mean? This it doesn't have to be this way. Although I think that is the easiest way to interpret such a thing like this, right? Okay. So that is the new price after the discount, this function. And t of x equals 1.10x. What could this mean? What could you need to understand that? What could this mean? Well, it can represent the tax on anything you pay in this store. If you pay this price, then they're gonna apply a tax of 10%, right? That's what this means. You're gonna pay 10% more, right? If you're gonna make a purchase of $100 in here for whatever things you're buying, then you're gonna multiply that by 1.10. That's gonna be $110 that you're gonna pay overall. Okay, and this takes into account the thing that you're actually paying for and the tax, the 10% tax in this store. You see? So that's these are the interpretations that I'm giving to t of x and d of x, these component functions. So first, I mean, in the end, how much are you gonna pay when you buy a TV whose original price is X? Okay, the first thing that the owner of the store is gonna do for you is gonna make the discount of $25 over the original price. Now this represents the new price for the TV after the discount, and finally multiply that by 1.10 due to the tax. And overall, all of this operation is gonna mean the total amount of money paid. That's the interpretation, and that settles the question A. Now let's talk about B. Question 1. How much did you pay for the TV before tax? Before tax, if the price tag was 699.99. Okay, then in here they're telling you the original price tag, or the original price, is this much. And basically they're asking you how much are you going to pay before tax. Before tax. So basically you're going to use this function, the function discount. Okay, going to use this, and you're going to evaluate it in this price. So how much are you going to pay? You're going to pay this much money minus the $25 discount, period. That's it. Number 2, how much did the TV cost after tax? Okay, then take this number and multiply it by 1.10. That's it, right? Just take this function t of x equals 1.10x, input in here this amount of money. I'm just gonna round. I'm gonna say 700 minus 25, and that's gonna be 675. I'm rounding because this is pretty much $700. So you're gonna evaluate the function t in 675, and that's gonna be equal to 1.10 times 675. And whatever number this gives you, that's gonna be the result of the second question. And that completes the letter B. And finally, C. The store offers insurance on the TV for, I'm gonna round again. I don't wanna, yeah, let's round. It's just simpler. For $50. If they cannot charge tax on insurance, rewrite P of X to include this fee. Okay, then P of X should be the same as before. Okay, the tax is only applied on the discounted price. You see, the tax is only applied to the discounted price, and then you add the $50 for the insurance. But this tax is not being applied to the insurance like they told me. So this would be the result of letter C, question 1. That's it. And the second question, use the new function p of x to calculate how much you paid with the insurance if the price tag of the TV was this much, 526. So just evaluate P in $526. And that's it, right? Just to make the evaluation, 1.10 times 526 minus 25 plus 50. And whatever number you get at the end, that's going to be the result. And that's it, guys. That settles this problem number 2. I'll make a little pause and come back. Okay, same section, section 2H, problem number 3. This one is interesting. It says create a word problem that can be modeled using the function f of x equals 0.75 times x minus 250. Define the variables and state a reasonable domain for your function. Okay, let's address that first. We're going to talk about b in a moment. So this is the function, guys. They're giving you a function and they're asking you to create. You can make whatever thing you want. That a situation in real life or otherwise that can be modeled using this function. Like give a real world interpretation of this function. Whatever you want, as long as it makes some sense. And this reminds me of something I told you in the previous exam, actually. Okay, what I did for this one, I'm gonna give you 2 examples so that you understand how this problem creation can be done. Look, I define this variable x is gonna be equal to the grams, so that's a quantity. It can be measured with a number, the number of grams of food ingested by a rabbit in a day. Okay, so I have a little rabbit, and this rabbit ingests, takes in some food, some grams of food. Okay, that's what x means to me. So I missed the domain here because if I define x in this way, then x has to be clearly greater than 0, right? Greater than 0, greater or equal than 0. And what is f of x? Is the weight gained in that day. The weight gained in that day. And now let's understand why this situation can be modeled by using this function. First of all, I don't know. I have no idea how much food, how many grams of food a rabbit can take in a day. This is all made up, guys. This is made up. I'm having a lot of hypotheses, right? Okay, what is the first hypothesis that I'm making? My hypothesis 1 is that if the rabbit takes in 250 grams in a day of food, okay, then this is going to be 0, right? And then this times 0 is 0. And what that means is that the weight gain in that day, if the rabbit, let me write that down. If the rabbit took in 250 grams, then the gain is 0. The weight gain is 0, right? Because there must be a balance. This could be understood as the minimum amount of food ingested by this organism so that it keeps the balance in its weight, right? And we all have that, right? I mean, we humans ingest about, I don't know, 2 or 3 kilograms of food per day in order to keep our weight. I mean, give or take. Maybe I'm exaggerating. But that's the first thing this is my first hypothesis. And anything above 250 will make the rabbit gain weight, right? And anything below 250 will make the rabbit lose weight, because that would be like, if this number is less than 250, this is going to be a negative number, and times this, it's going to be a negative number. So you're going to have a weight gain of a negative number, and that needs to be interpreted not as a weight gain, but as a weight loss. You see my point? So that's all it is, guys. That's all it is. And then B tells you state the component functions. I already did. Well, kind of. I'm gonna do that in yellow. My component functions are this. This is my first function. I'm gonna call it G. G of x equals x minus 250. And the function f equals 0.75 times x. These are my component functions. Oh no, I cannot call it f because I already have f in here. Can you see? This would be incorrect, guys. I need to label it with another symbol, maybe h. Okay, so if I make this composition g of, I'm sorry, h of g of x, h of g of x, that's going to be equal to 0.75 times x minus 250. And therefore, h of g of x is equal to f of x. So f of x equals h of g of x. In other words, f is a composite function. And let's interpret both g and h. What are they? What is the interpretation of these two functions? Let's first take a look at g. X minus 250. What does this mean? This means the number of, listen very carefully, x minus 250 is the number of grams ingested by the rabbit above its balance, its balance quantity. I'm going to call it that way. Let me say this in Spanish. Esto representaría el número de gramos de comida ingeridos por arriba de la cantidad crítica de balance. Se escucha un poco raro, lo sé, pero traten de entender eso. ¿Qué significa? Esto no significaría la cantidad de gramos que el conejo come, porque ya definí eso como X. X es la cantidad de gramos de comida que el conejo ingiere. ¿Qué sería X menos 250? Sería la cantidad de gramos de comida que el conejo ingiere por arriba de su cantidad crítica de balance, la cual ya dijimos que es 250 gramos. Si el conejo ingiere esta cantidad, en un día su peso permanece balanceado, o sea, ni gana ni pierde, ¿sí? Y cualquier cosa por arriba de esa cantidad le haría subir peso, y cualquier cosa por abajo de esa cantidad le haría perder peso. Entonces, ¿qué es X menos 250? Sería la cantidad de gramos de comida ingerida por el conejo por arriba de su cantidad crítica de balance. Así le estoy llamando. No sé si así se diga en biología. Cantidad crítica de balance. De peso. Suena muy técnico, pero bueno. Y luego, ¿qué sería h de x? Sería la cantidad de peso que gana por cada, y esto va a parecer trabalenguas, la cantidad de peso que gana por cada gramo de comida ingerida por arriba de la cantidad crítica de balance. ¿Sí? Ahí va de nuevo. Es toda esta operación 0.75 por X significaría la cantidad de peso ganado o perdido, ¿sí? Depende de si esto es un número positivo o negativo. La cantidad de peso ganada o perdida por cada gramo de comida ingerida por arriba de la cantidad crítica de balance. ¿Y cuánto es esto? Bueno, es 0.75 gramos, perdón, 0.75 gramos de peso por cada uno de esos gramos que estamos hablando. ¿Sí? Está un poquito técnico, pero creo que se entiende, ¿sí? Let me go back to English. Okay, and so that's it, guys. That's it. You see, I made this up. I made this situation up. Okay, nothing in this problem tells me that I should do this. It's just a creation. It was just a creation of my mind. That's it. That's it. Let's go to another example. Same function. Same function. And now I'm gonna create this other variable. X is the number of magazines sold. Let's suppose this, guys, that I wanna have a, I don't know, in CDEP, there is this student, right? And I don't know, he writes. He wants to be a writer in the future, and so he already has some stories to tell to the whole students in CDEP. And in order to do this, he wants to print some magazines with his stories. Okay, and he's gonna do the whole thing on his own. He's gonna use his money and all these things, okay, in order to print the magazines and sell them. Okay, now I'm gonna define X as the number of magazines sold. Number of magazines sold by this student. Okay, and I'm gonna say that f of x is the net profit, the net profit after after the sales. Okay, after selling x amount of magazines, right? And let's see what this. Let's analyze this thing. First of all, why do I say that the domain of this function should be greater or equal than 0? Because you cannot sell a negative number of magazines, right? It's pretty obvious. You can sell either something greater than 0 or nothing, which would take care of the equal sign. Okay, so this is the domain of my function. Now, let's analyze what would happen, guys. What would happen if this guy sells nothing? Like nobody's buying his magazine. Imagine that x equals 0. If you put this into f, what are you going to get? You're going to get f of 0, which is 0.75 times minus 250, which is a negative number, right? I don't know how much this is. This is okay. It's minus 200. It's minus 200. And what is the interpretation of this? F of 0 is minus 200. How can I interpret this in just normal language? The interpretation of this could be the following. That the net profit of this guy when he sells nothing is minus 200. And that means, guys, in my opinion, what the interpretation of this could mean is the total amount of money that he invested on this project, and that he has to recuperate. You see what I mean? He spent, in order to print the magazines, in all of that process of the ink and the paper, and maybe renting the printers. I don't know. He spent $200. So if he sells none of those magazines, he's gonna be $200 short than before the project took place. When the project took place, like he printed the magazines here, he is at a balance of minus $200 because that was the investment that he made, and he needs to recuperate that stuff, $200, and then anything beyond that is gonna be like net profit, right? Which he wants. Okay, that's what that means, guys. That's what this could mean. You see? Now, what happens if he sells exactly 250 magazines? Okay, what if he sells 250 magazines? Then f of 250 is gonna be 0.75 times 250 minus 250, which is 0, and that's gonna be 0. Okay, f of 250 is 0. What is the interpretation of this? That he actually needs to sell $250 to get square. You know what I mean? Like to not have lost anything in the project. There's a word for this, but I forgot it. Like sí, o sea, recuperó todo lo que invirtió. Hay un término preciso en economía para esto, pero no lo recuerdo ahorita. Él tiene que vender 250 revistas para al menos no estar en números rojos. ¿Sí? Eso es lo que significa esto. Eso es lo que significaría todo esto. Okay, and then anything above 250 is gonna make him some real positive profit. You see, any number of magazines above 250, and that's what it means, guys. That's what this means. Now, what is the interpretation of 0.75 in this case? That is the price of each magazine. You see, that's how much it cost him to produce each magazine, and that's gonna be the price that he's gonna be recuperating after he sells more than 250. Okay, if he sells 250 magazines, 251, I'm sorry, 0.75. If he sells 251 magazines, then he's gonna be making 0.75 times 1, 0.75 cents. No, $0.75. Okay, if he sells this many magazines, you see. So that's what it means, guys. That's what this means. In order to create a word problem, I mean, yeah, it takes some time. It takes some time. You need to. This is actually the difficult part of mathematics, to use your creativity in order to interpret a function and all these things. This is the the most difficult part, actually, because it involves not only understanding these things but actually making things on your own, like be creative with math. And yeah, it could be a little tricky. Okay, I gave you just two examples. There could be millions, and all of them could be right as long as they make sense, right? So that takes care of section 2H. You will make a pause and I'll come back. Okay, now on to exercise 2I. In this exercise, or in this section, you told me to solve 4, 5, 6, and 7. So let's talk about 4. For each function below, state the domain and the range of its inverse. Use your calculator if necessary. They give you 4 functions. In here, there's a typo. This is not supposed to be or. This is supposed to be for. For x greater or equal than 1.25. And the rest are 2, 3, and 4 are okay. What I mean is they are correctly written. Okay, so problem number 4. I need you to understand this deeply. What is the relation between the let me between the domain and the range of a function f and the same things, the domain and range of its inverse function? If you have a function and if you have its inverse, is there any kind of relation between their domains and their ranges? The answer is yes. The answer is yes. The domain of f is going to be the range of f inverse, and the range of f is going to be the domain of f inverse. Okay, that's all you have to do, guys. You have to switch. And why is this true? Why is this true? Consider this example. Consider this function f. This function f is represented by just a set of ordered pairs, 3 ordered pairs, 1, 2, input, output, 2, 4, input, output, and 3, 6. Once again, input, output. Okay, and that's just a function, right? It's a function. Let's consider the domain and the range of this function f. What is the domain? Is the set of all the inputs by definition, right? That's what the domain is. So the domain of f in this case, the domain would be the set of all the inputs. What are all the inputs? 1, 2, and 3. That's it. 1, 2, and 3. What is the range of a function? By definition, what is the range? Is the set of all its outputs. What are the outputs in this function? 2, 4, and 6. So that's it. That's the range of this function. The domain of f is this much. I mean, it's this, and the range of f is this. That's it. So far, so clear, right? Now, let's consider f inverse. Okay, what is f inverse? F inverse has to be this, guys. 2, 1, 4, 2, and 6, 3. If you notice, basically I'm switching the coordinates on each pair. 1, 2 now becomes, let's say it becomes 2, 1, 2, 4 becomes 4, 2, and 3, 6 becomes 6, 3. Why do I have to do this? Because that's what f inverse does. You see? What f inverse does is it takes a given output, of the original function f. Okay, so in here f inverse is taking such output, this output, and it's taking it as an input. In here, this is the output of f for this particular value of 1. For 1, f gives you 2 as an output. Now give that output to f inverse, give it as an input, and f inverse should do the reverse process, right? It should give you back the original input with which you started. You see, remember that that's what the inverse function does for you. It reverses the process. It reverses the process. If you have f, and if you have f inverse, right? And if you give, once again, if you give the value of 1 to f, and f outputs the number 2, then f inverse, by definition, has to do this. Take the number 2 in and output the number 1, which is the same stuff with which you started. And f inverse has to do the same type of behavior. It has to present the same type of behavior for any other value in f. Okay, if you give f the value of 2 and it outputs the number 4, then f inverse should take the number 4 and reverse the whole thing and give you the number 2 in return. You see, that's why in the representation of ordered pairs, this should happen. Each of these pairs is reversed in this way. Okay, perfect. So now, what do you observe, guys? If you take a look at f inverse on its own, forget about f for a moment. Just take a look at f inverse on its own as a function, regardless of whether this is the inverse function of something else. Just take a look at this as a function. Then what is the domain of f inverse? Once again, it's the set of all its inputs, which is 2, 4, and 6. 2, 4, and 6. And what is the range of f inverse? Is the set of all its outputs, which is 1, 2, and 3. 1, 2, and 3. And what do you observe? You observe that the domain of f is the range of f inverse, and that the range of f is the domain of f inverse. You see? And that's going to happen always, whether you represent a function in ordered pairs, as an equation, as a graph. It doesn't matter. The same thing holds. Okay, now that you have understood that, let's address some of this, right? Let me bring in Desmos. Continue. So each of these functions, guys, 1, 2, 3, and 4, I'm plotting on Desmos, and they are right here, as you can see. You can check. Oh, I made a mistake in here. This is supposed to be a 2, like this. Yeah, I think that's correct. Okay. Okay, so the first thing in here is, remember, guys, this function is telling you that it only works for x greater or equal than 1.25. You should only consider values of x greater or equal than 1.25. And how do you do that in Desmos? You put braces, and you write that statement: x should be greater or equal than 1.25. If you don't do that, if I delete this thing, then Desmos understands that I can work with any value of x, right? You see, which is okay, right? Because the largest domain for this function is all the real numbers. If you give any real number to x in this function, nothing weird is going to happen. No divisions over 0, none of that stuff. But if you consider this function as it is, with the largest domain possible, then this function has no inverse. If you want to talk about its inverse, you should remember, you should take just a part of the domain. Okay, for example, this part that goes from 1.25 onwards, or from minus infinity to 1.25. In the book, the authors decided to go for the first type, 1.25, the right branch of the parabola. And now this actually is a function one-to-one, and it has an inverse, right? Okay. And what is the inverse function? I'm not gonna isolate. I'm not gonna find f inverse, because if you realize they're not asking you to find f inverse, guys. They're asking you to find the domain and the range of the inverse function. If this is f, and if you know that the domain is all the numbers greater than 1.25, let me write that down. Okay, we're talking about this example at the moment. The domain of f is equal to um, 1.25 up until infinity. This is the domain from here onward. And what is the range? Well, just take a look at the graph. It begins in the y-axis. It begins in 1.875, and then it goes upward. You see, the minimum value of the output, or the y, is 2.875. So that's what I should write in here. 2.875 onwards up until infinity. That's the domain and the range of f, but they are not asking you for this domain nor this range. They're asking you for the domain of f inverse and the range of f inverse. But if you understood what I told you a moment ago, then you have the problem solved. If you know the domain and range of the, let's say, the original function, then you know the domain and the range of the inverse function. What is the domain of f inverse? Is this. Just write it down. And what is the range of f inverse? Is this. Just write it down. That's it, guys. That's all you have to do. So for the original functions, find the domains and the ranges by looking at their graphs. And then if you do that accurately, then just reverse domain for range in order to get the domain ranges of the inverse. Let's just do one more. What about this? Take a look at this. I'm gonna zoom out. Is this a one-to-one function? Yes. Yes, it is. Okay. What seems to be the domain? Let me zoom out. The domain is gonna be all the real numbers. Okay, because you can give, I mean, basically, why? Because you can give any number to x and nothing weird will happen. Nothing weird. You can always calculate 2 to whatever number. You can always do that. So the domain for this function that we're talking about is all the real numbers. And the tricky one might be the range. Let's take a look at the graph. Okay, take a look at the graph. Let's zoom out. It's actually tricky to find out, but if you notice, this graph will never go, like, this is the number 3, right? You got 2, 3, 4. Take a look at the number 3, and notice that the graph never goes below. Let me zoom in. You see, this is number 3. Take a look at this horizontal line, which represents the number 3 for the output, and notice that the graph never goes below that value. Never. No matter how much zoom in you take, like, can you see? It never goes below that one. It gets really close. Really, really, really close. Can you see? This is the number 3 once again. This gray line. And the graph never goes below that value. Never. You can do this forever, and that's never going to happen. So conclusion is the range of this function f is all the numbers from 3 to infinity, and not including the number 3. Why? Because this graph, the red graph, never touches actually that number 3. And you can spend a lot of like, you can do this more and more and more and more, and you will notice that it never touches it. So the number 3 should not be included in the range. Okay, that's it. So domain of f done, range of f done, then the domain of f inverse should be this 3 comma infinity, and the range of f inverse is all the real numbers, period. That's how it works. And I'm going to stop it right there. Number 5, create a one-to-one function. State the equation of the function and of its inverse and explain why the inverse is also a one-to-one function. Let's use Desmos for this too. I mean, you can do something as simple as this, guys. That's it. F of x equals x plus 1. This is a function f. I can find its inverse very simply as f of x equals x minus 1, right? By the process that you know by now, f inverse. So this is the equation of f, this is the equation of f inverse. And why is this also a one-to-one function? Because how can I explain this to you? I mean, in order for this function to have an inverse, it has to be one-to-one. One-to-one. I think the symbol is actually this one, guys. If I'm not mistaken, it's one-to-one. You're gonna find sometimes this symbology, one-to-one. This is a one-to-one function, and so it has an inverse. What is its inverse? It's this much. It's this one. And why does this have to be one-to-one? I'm finding trouble explaining. Let me think up of a good explanation that you can find easy to understand. Give me a few seconds. Okay, this is gonna sound once again a little tricky to understand, so I'm gonna say it very slowly. Okay, look. If f is one-to-one, it has an inverse and it can be found. And this is it. This is f inverse. We had demonstrated that before. Okay, so if f is one-to-one, then it has an inverse, f inverse. Okay. And what does that mean? That means that f inverse undoes what f does. But by doing this process, guys, we have to understand that f inverse also has its own inverse, which is this, right? Okay, and by saying that, by saying that f inverse has itself an inverse function, then I am saying that this has to be one-to-one. Now, that's not a very good reason, but I mean, I'm thinking of telling you a more technical explanation, but I don't know if I'm gonna get you confused. Let me think a little more. Just give me a moment. I already found a way to explain to you guys why f inverse has to be one-to-one. Once again, let's work out the whole. Let me redo the whole thing for you in here. Once again, what is the question? The question was creating a one-to-one function. I already did, which was f of x equals x plus 1. This is a one-to-one function as demonstrated by taking a look at Desmos, right? And I found its equation. I mean, I created the equation and then I found the equation of its inverse. So far, so good. And then this is the difficult part. Explain why kind of difficult. Explain why the inverse is also a one-to-one function. Okay, here is the argument. And this is kind of cool because I'm going to be showing you what an argument. This is really nice. I hope you understand this. Argument by contradiction. This is one of the coolest things in mathematics, guys. This concept, an argument by contradiction, or I mean, it's usually known as proof by contradiction. It's really cool stuff. Proof by contradiction. Here it goes. Look, any function, the first thing we have to understand is this: any function, regardless of if this function is an inverse or not, doesn't matter. Any function, if you call something a function, then f is either 1 to 1 or many to 1. There are no other possibilities. Any function is either 1 to 1, and if it's not 1 to 1, then it has to be many to 1. Okay? All the functions can be classified in either one or the other. If one function is not in this classification, it must be in this classification. If one function is not in this classification, it must be in the other one. Okay? Perfect. And that holds for any function whatsoever, any function. So this function f inverse is, since it's a function itself, then it must be either 1 to 1 or many to 1. Okay? And this is the cool part, guys. This is the cool part. I'm gonna do this. This is where the whole thing of contradiction comes into play. I'm gonna demonstrate to you that f inverse, if I assume that it can be many to 1, that's if let me write that down. If I assume that f inverse is many to 1, this leads to a contradiction. It's gonna lead me to a contradiction. Okay, what is the contradiction? It's this. Look, for simplicity's sake, let's say this: that f inverse, this f inverse is many to 1, and what that means is that f inverse is gonna look something like this. If I treat this f inverse as a set of ordered pairs, it's gonna look something like this. It's gonna have at least 2 pairs that tell me that this is a many to 1 function, right? This is many to 1, but by having these 2 pairs. Why? Because both 1 and 2 go into 3. You see, these 2 inputs, 1 and 2, both go into 3. That's what makes a function many to 1, right? Many inputs, in this case 2, go into just 1 output. So therefore, this is a many to 1 function. And by the way, I'm not saying that these 2 pairs are in fact that these 2 pairs of coordinates belong in this function. They don't. I'm just making things up. But if I assume that f inverse is many to 1, it's gonna look something like this. It's gonna have 2 pairs for which different inputs lead to the same output. Okay, fine, perfect. And this is where the contradiction happens, guys. If this is f inverse, then f should be written like I showed you before. If you want to write f, all you need to do is change the order of the coordinates. So this one becomes 3, 1, and this one becomes 3, 2. And we don't care about the rest of the pairs. So I'm just gonna write 3 dots. And this is where the contradiction happens. Take a look at this. What does this tell you? This tells you the following: that this set is not even a function, because this same input of 3 leads into 2 possible outputs, 1 and 2. You see? So this basically, by saying that f inverse can be many to 1, and by writing down this example, then this leads to the writing of f in the following way. And this wouldn't be even a function. This is not a function. And we already established that f is in fact a function. That is, we're contradicting ourselves. The contradiction is that if I assume that f inverse is many to 1, such an assumption leads to this contradiction, that f would not be a function in the first place. You see? But we know that it is. That's one of the first assumptions, that f is a function. That's what this thing is, guys. Proof by contradiction. If you prove that an assumption, leads to an absurdity, to a contradiction, then you have to say that the assumption is false. Okay, so f inverse cannot be many to 1, and if f inverse cannot be many to 1, okay, if f inverse is not this, then it must be 1 to 1. You see, this is a very elegant way to prove things in mathematics, proof by contradiction. I hope you understood the gist of it. I'm gonna show you this technique later, maybe in the next semester or later, because it's a very pretty technique of demonstration. It's pretty cool. So I hope you understood this thing. 5. Okay, let me make a stop. Now let's actually continue. F of x equals to 2x minus 5. Solve this. Well, that's quite simple, right? If f of x is this much, then solve this. Then all you have to do is this. And I'm gonna be solving, x is gonna be 8. That's it. So f of 8 is gonna be 11. That's letter A. B, find f inverse of x. Find f inverse of x. That's gonna be it's gonna be x plus 5 over 2, right? Am I right? Yes, that's it. F inverse of x is equal to x plus 5 over 2. Of course, you're gonna be doing the whole thing, the whole process, right? Let me check. I'm a little sleepy, and I need to check. Y equals 2x minus 5, y plus 5 equals 2x. Yeah, that's right. This is f inverse. Done. C. Well, let's do it here. Find f inverse of 11. Well, it's going to be 11 plus 5. 16 over, it's going to be 8. F inverse of 11 is 8. What do you notice about your answers to parts A and C? They are the same. It's 8. X equals 8, and f inverse of 11 is 8. Create a general rule to explain your answer to part D. Well, I mean, it's what we have been knowing for the whole time, right? That's what f inverse does. F inverse, what happened, guys, is that in the first part, in here, we found that f of 8 is going to be 11. F of 8, input, output. And if I know this, then I know immediately that f inverse, if I calculated f inverse, and if I evaluate it in this output, then the result is going to be 8, which is the original input. Original input goes into this output, give this output to f inverse, and f inverse will convert it back to the original input. You see, that's what we have been knowing all along. I don't know why they put this problem. It's very simple. Okay, that's what f inverse does. It reverses the whole thing. And I mean, that's it. I mean, I don't understand the purpose of this problem. Anyways, 7. Given f of x equals minus 2x minus 1, and g of x equals minus 3x x squared. Show that G composed with F inverse of -1 is 0. Okay, so this can be also written as G of F inverse of -1 is 0. Okay, I need to show this. I need to show that this is true. So I need F inverse, right? Because they just give me F. So this is F minus 2x minus 1. I convert f of x to y. I isolate x. That's going to be y plus 1 over minus 2. That's x. And therefore, finally, I change x for, well, let me write it in this way. And I change x for f inverse of x. And I change y for x. X plus 1 over minus 2. So this is f inverse. I already have f inverse. Okay, fine. And then I'm going to do the rest in here. This is not the way you should work, like from here and then here and then here. But since I'm telling you, then I guess it's okay. The first thing I did, the second thing I did, and the third thing. I'm going to do the third thing in blue. I'm going to evaluate f inverse in -1. This is f inverse, and the evaluation in -1 is straightforward. That's going to be 0. Do it, please. Evaluate this function in -1, and you're going to get 0. And then evaluate g in 0. G in 0 is going to be 0, right? Because take a look at this. -3 times 0 to the square is going to be 0. And that's what you have in here. So g of f inverse of -1, that's going to be 0. This was also quite straightforward and simple, actually. Let's continue. Exercise 2J. From there, you told me problem 3 and problem 4. Problem 3. Show that f of x equals this thing, minus x minus 2 over 5x plus 1 is a self-inverse function. What is that, a self-inverse function? We say that f is self-inverse if f inverse is the same as f, which is this is not true for all functions, guys. Okay, only for a specific set of functions we have that a function and its inverse are actually the same function. Okay, which is the case for this one according to this problem. Let's show that. This is f of x. Let's find its inverse. How do I do that? Remember, we revert to write y instead of f of x. We write the whole function like so, and then we isolate the x variable now. So let's do that. This is just basic algebra. I need to isolate x. Remember, that's my goal. So this is going to be 5yx plus y equals minus x minus 2. 5yx, I'm going to bring this here, plus x. I'm going to take this and put it on the other side, minus y minus 2. Then I'm going to factorize the x. 5y plus 1 equals minus y minus 2. And finally, I divide both sides over 5y plus 1 minus y minus 2 over 5y plus 1. And once I'm done with the isolation of x, I write f inverse of x instead of x, and I write instead of y, I should write x. And there you go. This is f inverse of x for this function, for this original function. So indeed, the inverse function to this function is in fact the same thing. Can you see? It's the same function. They are the same function. So f is equal to its inverse. And when that happens, we call f a self-inverse function. A self-inverse function. And that's it. And number 4, find the value of m such that g of x equals all of this thing is a self-inverse function. Okay, so let's write g of x equals 2x minus 4 over x plus m. And let's find its inverse. Once again, I'm gonna do the same process. Just follow the algebra. Wait, let me check if I'm doing everything right. Right. Okay. All right. Yes. Okay. Mm-hmm. And I'm gonna finish in here. F inverse of x is gonna be equal to minus xm, or let me write down minus mx, minus 4 over x minus 2. Okay, so this is f inverse of x, right guys? So I'm sorry, it's not f inverse, it's g inverse. G inverse of x is equal to this, and g of x is equal to this. Take a look at them. Take a look at g of x, it's this much, and take a look at g inverse of x, it's this much. And the question is, find the value of m so that this is a self-inverse function. In other words, such that g inverse is the same as g, because that's the definition of self-inverse. If this thing is the same as g, then g is a self-inverse. In other words, if this is the same as this, then and only then g is a self-inverse. So take a look, guys. Take a look. Just take a look. What this tells me, look at the denominator here. Look at this denominator, x minus 2, and look at this denominator, x plus m. If m is equal to minus 2, give m the value of minus 2, okay, in here and in here, and you're going to notice that they're going to be the same. In this case, it would be minus 2 times x minus 4 over x minus 2 if m is equal to minus 2. And in here, you will have x minus 2 in here. 2x minus 4 over x minus 2. Right? And so look at this, and then take a look at this, which is minus times minus. That's going to be 2x minus 4 over x minus 2. You see? So basically, I need to make this thing exactly the same as this thing by choosing a proper value of m. And by looking at the denominators, x minus 2 and x plus m, then I get the glimpse, or I get the clue that m should be minus 2, so that the denominators are the same, right? And then, okay, let's assume that m is minus 2. Substitute in the proper places, which is right here and right here. And if I do those substitutions, then this becomes this, and this becomes this, and therefore you can see that both things are in fact the same. So m should be -2 in order for this to happen. Okay, um, and that's it. That's it, right? I'm gonna finish the whole thing right here, guys. I think you told me to solve some of the chapter review, but I think that's about it. That's 1 hour. That was enough. Don't worry about the problems from the chapter review. They're not gonna be that complicated in the exam. Okay, thank you guys. Sorry about taking so long to upload these problems. Have a good day.